Alright folks, so this week we're going to look at using analog values with our microprocessor. Analog is a little bit different from digital. With digital we saw we could have things be on or off. They were either high or low, with 0 or 1, but that was it. There was not a lot of granularity there. Analog gives us more granularity across the spectrum for an input or an output. It is still, in fact, digital, but there's more steps. So instead of being 0 or 1, our analog inputs, for instance, are 10-bit. So they can be a value from 0 to 1023. Our analog outputs that we use with pulse width modulation, or PWM, are 8-bit, so they're 0 to 255. And we'll see what that means. What it lets us do is things like dim an LED. So rather than the LED being on or off, we can dim it. Or we can read the input from like a range sensor to see how far away something is, not just whether it's there or not. So to start out with, I am going to add some comments into my code for what I'm going to need to do here and what I want to do. And to start out, I'm going to read an analog sensor, and I think I'm going to start with the light or photo sensor, and then I'm going to adjust or set the brightness of the LED. So the Circuit Playground Express has a lot of built-in sensors and output options, which is great. It makes it really convenient because we can do a lot of stuff just on the board without having to worry about connecting anything else. So for instance, there's a photo sensor here, the little eyeball. There's a temperature sensor over here. These two have our pin numbers next to them, A8 and A9. So those are analog pin 8, analog pin 9. They're connected directly to our microprocessor, so they're always available to us on those 8 and 9 pins. Those are not on the outside ring anywhere. We're going to have a conflict with them. The other stuff on here, there's a audio sensor like a microphone on here. There's an accelerometer. Where's the accelerometer? Here. That does like tilt and rotation. We can measure that. So there's a lot of stuff, and then we've got the Neopixels for output is what I'll be using today, and then the normal LED on pin 13. Okay, so let's look at this. So I want to read the light sensor here, the photo sensor. That's going to measure like the light or the dark. So if I cover it up, it'll be dark. You can see the shadow covering that. And it's going to give me that value 0 to 1023 as a measure of that light. And that value, the pin is reading voltage, right? So it's actually that 0 to 1023 is a representation of the voltage that it's receiving from that sensor. And then we'll use the LED again. So to do all of this, what do we need to do? Well, let's start out with, we're going to include our library up at the top. And I said we're going to use that LED pin. So I'm just going to do const in LED pin is 13. And I'm going to set my pin mode for that LED to output. I'm going to start the serial connection so I can debug. And I'm going to add something in here too that you might see around. I'm going to say while not serial. So what this is doing, so a while loop is another kind of loop, like our for loop, that's going to loop for some condition. So it's like combining a for loop with an if statement. And I'm saying, well, not serial. That's the equivalent of saying, well, serial equals false, or well, serial equals 0. So the serial class, if I call just the serial class, it's going to check if the serial port has been opened and is ready for communication. Okay, so that takes a moment of time on the microprocessor. And if we're going to start doing stuff with serial right away in our code, we might want to wait until that port is available before we proceed. So what this while loop does is it's basically checking for a double negative, right? It's saying, so while serial equals false is true, loop. So it's potentially creating an infinite loop, right? Like if the serial port never establishes, that's going to get stuck there and nothing else after that is going to run. It's going to be like a holding pattern. But as soon as serial is true, this condition will be met. So while serial is true, or if serial is true, then not serial is false, right? So then that's going to break this loop. So as soon as serial is true, the loop breaks. If we did this, this is the opposite of that, right? So while serial is true, once our serial port connection is established, then we'd be stuck in the loop, and we really don't want that. So we're going to say, well, not serial for checking basically the falseness of the serial connection. All right. And then what? Yeah, I need to initiate the library too. Like that. Okay. And that's going to be it for my setup for now, I think. To read an analog sensor, very similar to a digital sensor, I'm going to declare a variable here, int light equals analog read, and I give it the pin number. And I said I looked at the board, that's A8. So for these analog ones, we actually put the letter A in there, A8. That's how it knows it's the analog pin and not the digital pin. And that's it. And that's going to read our light value. And then I can say like serial.println light to see what that value is. So one other thing I'll mention here before we try this out, you'll notice I'm putting my int light here. I don't have it up here as a global variable because this value, I'm replacing it every loop. I'm not like storing something there that I'm concerned about losing, so that's fine. I don't need it to be global. But to mention something about scope here, this variable that I've declared in loop is only available within loop, right? So for instance, if I check this code, I have to save it. And that's fine, it works. If I put something in here like light equals 8, I'm going to get an error. Right, it's going to say light was not declared in this scope, right? So while light is declared here, that's within the scope of loop. Within the scope of setup, there hasn't been any light declared, right? So I could say something like int light equals 8, and then there would be a light within this scope, which is different from the light within the loop scope, okay? So that can be a little confusing, so I generally will try to like keep my variable names unique. If I wanted the same variable to be available in both of these scopes, that's where I'd want to use a global variable up here, because things up here are outside of setup and outside of loop. Then everything lower than that level, they'll be available too. Okay, so let me get rid of that, and let's upload this. It's going to take, you may have figured out here, this is just some of the example code they have that I've been running that's using the sound sensor to detect volume. So as I'm speaking, it's making the LEDs a volume meter of my voice. But we'll get rid of that. And check out the serial monitor. And we're getting a fast stream of values in the 200 level. And so you can see right away that the analog values have some noise to them, right? Like, I look over here at my circuit playground, it does not appear to me that that light level is changing that dramatically. It's going from like 270 down to 250 to 230. There's a lot of fluctuation there. But we can still see gross movements or gross changes, right? So as the shadow comes over the light sensor, it goes all the way down to 10, 11, 12, versus something in the 200s. And if I actually pick this up and move it towards the lamp, I can get it up to the 900s, right? And then slowly back down to the 200s when it's on the table. So it does in fact have a broad range, but there's a lot of noise in the system. So that's something to keep in mind, as is that range. So like the default range for this is the default like setting that we get is gonna be different based on the location where you set this up, right? So you have to be very mindful of that as well, particularly something like a light sensor. If I have this in a setting, right, where there's a window and light comes in through that window during the day and not at night, then I can't rely on this 200 something value to be my default at all times, because it's going to change based on the ambient lighting environment. So I want to keep that in mind as well, and we'll look at that problem specifically a little bit later. Okay, so that's how we get our analog input value, and it gives us a lot more to work with than just the 0 or 1 from the digital read. Now, to set the brightness of the LED, again, instead of saying digital right, I'm just going to say analog right, and I'm going to say my LED pin and the value that I want to set it to. So now for my analog right, I can set a value between 0 and 255, right? I said it has a 8-bit pulse width modulation. What that means is that the light, the LED, is actually, it's not like if I send it the value like 127, it's going to get half voltage and be half dim, right? If the LED doesn't get enough voltage, it just doesn't turn on. It's not like a incandescent light bulb that we can dim. So we pulse width modulate it. What that means is that we are essentially turning it on and off very fast. And depending on the ratio of the off period to the on period, we can create a dimming effect, okay? It's very similar to like animation or film, where the frame rate is so fast that it tricks your eyes into thinking that the image is moving, right? When in fact it's just a series of still images. Same thing with the LED. The LED is either on or off, but it's blinking at such a fast rate that you can't see the blinks. It appears to be a certain level of brightness. So that said, I can immediately see I have a problem here, right? If I just put in light for my light value, and the light value goes above 255, I'm gonna have a problem because the analog write can't handle that. It will in fact wrap the number, but that's not the behavior I want. I need to scale this value of my light, which is 0 to 1023, to the range that is acceptable for my PWM. So I need one other thing here. I'm going to say int bright. So I'm going to make a new variable called bright for my brightness, and that's going to equal the map. So I'm using a map function here, and within the parentheses of the function I give it some arguments, and map takes a lot of arguments. We've seen other functions here, print, analog, read, they take 1 or 2. Map's going to take a lot. The first thing I'm going to give it is the value that I want to map or scale, and that's light from here. The next value is the low end of the input range. So that I said that it's an analog range, so it's going to be from 0, and then the next one is the high end, 1023. So that's the min and the max of my input range, and then I'm going to put in the range I want it to scale to, and that's going to be down here, 0 to 255. And so essentially the map function is going to do a fancy cross multiply, right? To take a value that's in one range and turn it into another range. The cool thing is that I could flip these around, right? So I could say 255 to 0. What that means then is like my value comes in. Let's say my light reading is 0. There's no light. It's going to say, okay, well 0 in this input range is equal to 255 in this output range. So it's going to give me a brightness of 255, so I'm flipping it. Whereas if I was at maximum brightness 1023, that would come in and be like, okay, that's max. Then it's going to give me a 0. But I don't want to flip it for this demo just yet. We'll use this. So now, if I have an input of 0, I'm going to get an output of 0. If I have an input of 1023, I'm going to have an output of 255, and everything in between will scale appropriately. So then instead of saying light, I'm going to say bright. All right, let's check that out. So it's not working. Why is it not working? Well, let's look at our serial monitor. All right, so we're still getting this 200 something level for our light, but let's also look at our brightness then too. So I'm going to change this from a print, and I'm actually going to move this from up there. So I've got my two variables up there, then we'll do our prints down here. And I'm going to do another print of a string \t, and that's going to give me a tab, which will help give me like some even spacing in my serial monitor so I can see some columns. And then we'll do our print line of bright. Okay. There we go. So we are getting a brightness value. And there we go. Now our LED's on. Huh. That's a bit odd. And you can see, as I move the shadow over that light sensor, the LED dims. And then it gets brighter when I move it away. And you can see, like, when the shadow's over there, our analog read value is in the teens, and our brightness value drops down to like 1 or 2, almost off. So that's pretty neat. So that's looking at how to read an analog sensor and how to output a dimmable LED or a pulse width modulation. And the temperature sensor in its raw data state works the same way. You just use A9 to read the temperature. There is a function in the library to convert it to Celsius, though. So if you want to check that out, just go into the examples. And I think that's in hello. Yeah, hello temperature. The other thing I want to look at right now, though, is the accelerometer. I'm going to leave all of this. What I'd like to do with the accelerometer, oops, and then I want to adjust the Neopixels based on that. I don't think I need anything else. So the accelerometer is also directly wired into the microprocessor, and to use it, we really need to use the library that goes along with it. Reading the raw analog values isn't going to do us any good. So let's look at how we use the library to do that. And we're going to need 2 new variables. I want the x and y values from the accelerometer. So an accelerometer measures like tilt, right? So if I tilt it side to side and up and down, that's the x and y directions. It also has a z, right, which is the this axis, I think, that you could use as well, but I'm just going to use 2 for now. And so I'm going to make 2 variables, but I'm using a new type here, right? I'm using floats. So I'm just going to say float x. And a float is a number that can have a decimal point. So like 4.5 is a floating point value, whereas the integers cannot have decimal places. And I'm going to use float just because I looked up in the documentation for this part of the library. The accelerometer gives us a float value. So float x equals circuit playground, so I'm calling the library and then the method motion x. And I don't need to pass anything to that. That will return the x bit of the accelerometer, and then if I do float y equals motion y, I'll get the y part of it. I'm going to add those to our serial output too. And so to do that, I'm going to put another tab under here, and we'll do print x, tab, print y. All right, let's just see what that does. Okay, so we've got 2 new columns, And if we tilt this, we go from positive 10 to about negative 10, and then in this direction we can go from about negative 10 to about positive 10. So that's the range that this one is working on. I'm not entirely sure why they wrote the library that way rather than using the 0 to 10, 23 values, but that's what we have to work with, so we will adapt. Okay, so that's my reading of the accelerometer. Now to adjust the Neopixels, I'm going to do something simple with my Neopixels, but I want to do the entire ring. I don't want to do it with like just one. I'm just going to do all of them all at once, so I have more light, more stuff I'm working with. It's a little more interesting. So to quickly work with all of them, instead of doing like set pixel 1, set pixel 2, set pixel 3, I'm going to use a for loop. So I'm going to say for int I equals 0 while I is less than 10, and then I plus plus for each of my Neopixels. Then I've got the curly braces, right? And you'll notice, like, whenever I make the opening curly brace, the Arduino IDE automatically puts in the closing one. That's very convenient. You always want to make, for every open curly brace, you need a close curly brace, and you want to make sure that they match the way that you expect them to, right? And I showed you this trick last time where it will highlight whichever one is matching there. So you want to keep that in mind. And then within this for loop, we'll do our setting of the pixels. And I need the library again. And so the number of the pixel is I, and then I've got our RGB values. Lord. Okay. And that's it. And then that will set all the pixels to the same color. And the color values here is what I'm going to adjust based on the accelerometer. The green one I'm just going to set to 0. We'll just work with blue and red. And for those colors, again, I'm going to need to do some mapping, right? The RGB values need to be 0 to 55. And I've got, what did I say, negative 10 to 10. So let's get some maps going, right? I need variables first. We'll say int r equals a map of my x from the accelerometer, which is going to be from negative 10 to 10, and I want that to be 0 to 255. And then my int b is going to be a map y from negative 10 to 10, 0 to 55. Okay. And so now with this map function, an important thing to know is that you can actually go beyond these ranges, right? So if I put in 11 as my x value here, that's outside of this range, it's going to give me a value above 255 for that. It'll be appropriately scaled, but it will be outside of the range. So keep in mind that you can exceed your range. So if it's important that this value like never exceeds 255 or something very bad will happen, then you want to constrain that value. But for this, it'll just wrap, so I'm not terribly concerned about it. All right, what does that look like? Okay, so we've got a purplish color, and if I rotate this way, we're getting very purple or pinkish. If we go this way, we get blue. purple to blue, and then if we do this, there we go, we get our red up there, and then we'll go back down to purple this way. And of course we can do whatever mix we want in the middle. That's not the best on the camera trying to capture the light, but run the code on your own CPE and you'll see how that looks. So I think that is it. We've looked at how to read analog values and how to use these values that are in larger ranges for different kinds of outputs and how we can adjust those ranges as necessary. Oh, one more thing I could show you real fast. One of the other there's a microphone on here, as I mentioned. We can read a value from that too. If I wanted to do something with that, I could say float m equals so this is like a library within a library. The mic has a whole slew of things that you can do with it, but we want the sound pressure level, which is the volume. And so to do things with sound, because sound is real time too, and it changes so quickly, there's often a lot of other signal processing and analysis that has to happen on the sound to get anything useful out of it. And so we often use samples. So we will actually like capture microphone data over a certain period of time, and that will become a sample set that we can use to analyze whatever it is, the pitch, the volume of the sound in that little bit of time. And that sample size, that can be incredibly short. That will be a fraction of a second for that sample. But we want some of these samples to average, basically. So I'm going to say, give me 10 samples to determine the volume. And let's just add that to the front of our array or list of values here. That was n. Another tab. Is that right? That's odd. Oh yeah, no. Oh boy, I forgot that the other serial prints are up there. Okay, yeah, so this one in the middle is the microphone, and you can see as I'm talking that we're getting some jumps in that value, and that its base level is down there around 5862. Okay, so that's looking at analog inputs and outputs.